Hello, Luke. Welcome to Lesson 81. So, as promised, today we are going to continue in the graphing world. And really, what we're going to do is take what we've learned in regard to graphing and apply it to systems of equations. All right, so up to this point, when they've given you a system of equations, such as what we see here, you would tackle this by choosing either the elimination method or the substitution method to solve for x or to solve for y, and then obviously solve for the other one, and then come up with a solution to these two equations. But today we kind of need to step back from that and look at the big picture again. So what is it that we were trying to do when we solve for these systems of equations? Recall, and we talked about this when we first introduced substitution and elimination, what we're trying to do is find some ordered pair, some x and y value, such that it will make this first equation true and also make this second equation true. And for all of the equations that they've given us up to this point, they've all been what we call linear equations, or equations in the first degree. And recall, degree just means what is the highest exponent of any term in the equation. So in this case, each term has only one variable, and that variable is to the first degree, so we would call these first degree equations. And whenever we have first degree equations in two variables, we're talking about a line. All right, so maybe you haven't noticed that, but I'm just going to point it out specifically now that all of these systems of equations, they've all dealt with equations that were equations of lines. All right, they never gave you something that looked like this. They never said, find the solution to this ordered or this system of equations. So maybe it's y squared plus x equals 12, and y squared plus x squared equals 3. Here we have all these exponents with these variables. These would not be linear equations. These would be equations in the second degree because the highest term is of the second degree. So again, they haven't given us any of these. They've only given us equations that are equations of the line. And then we have found solutions to these equations. All right. Today, we're going to look at kind of the illustrated version of this. Instead of using the substitution or the elimination method, let's actually use the graphing method to solve these. Because if they are equations of a line, then we now know how to graph an equation of a line. And what would the solution to these look like if we were to graph them? Well, let's experiment with this idea here. So let's take a graph here, and let's just graph these two out. We know how to do that now. So y equals x plus 1. Our y-intercept is at 1, positive 1. So we will place that on our graph here. And then we have our slope is 1 over 1. So we go up 1 over 1, up 1 over 1. We could just keep going, up 1 over 1. Okay, that is going to be the equation. And I didn't say it, I probably should have, but we note too that it's a positive slope because of the positive sign in front. So the positive sign in front of the x. All right, now let's look at the other equation. So the other equation, we have a negative 2x plus 4. All right, so how would we graph that? Well, where does it cross the y-intercept? It intercepts the y-axis at 4. So we go up to the 4, and we will draw our dot here. Oops. Draw our dot here. Okay. And then we need to say, what's the slope? Well, it's a downward slope, so we're going to be going downhill this time. And it's over 2, or I should say up 2 or down 2, over 1. So we're going to go down 2 over 1, puts us right here. Down another 2 over another 1, puts us right here. Down another 2 over another 1, puts us right here. So that is the line, the graphed line for our second equation. Okay? So, looking at this graph, I might ask you, what do you suppose the solution is to this equation? Now, we could use our substitution method or our elimination method to solve for this, but in this case, let's just look at the illustrated version here. What would be the solution? Well, remember, the solution is the x and y ordered pair that satisfies both of these equations. Well, the red line, anywhere on this red line, you pick a point on that red line, and the coordinates of that point will satisfy the equation for this first equation right here, right? Well, maybe I shouldn't write that in blue. We'll do it in red. So that would satisfy this equation, right? So if I just pick this point looks like it's sitting somewhere around, 1, 2, 3, 4, a -4 for the y, and a -5 for the x. So this is sitting somewhere around -4, -5. So if my guess, because this is a guess here, but if my guess is right, -5, -4 should be a solution for this equation, as well as this, or excuse me, it would be a solution for this equation. And actually, we could probably even plug that in. If I say -5 is the x, plug that in for x, -4 is the y, plug that in for the y, I have this +1 left over, and we can see that actually my guess is right on the money. -4 does equal -4. It is true then that this ordered pair is a solution for this first equation, right? And I can do that anywhere on this line. I can pick any point on this line, plug it into this first equation, and it should and will come out to be a true equation, all right? Those are all the solutions for that equation. Now, in like manner, if I go to my blue line, I can pick any point on my blue line, and I can take the coordinates of that point, plug it into this second equation, and that equation will be true. All right? So if we're trying to find in this system of equations the ordered pair that satisfies both of these, then we need a point that is on both of these lines at the same time. Okay? And there's only one point here that's going to do that, and that's this point right here, because this point satisfies the blue line. We're on the blue line. It also satisfies the red line. We're on the red line. Okay? It's the only point that will satisfy both. So this spot right here is going to be the solution to this set of equations. So looking at that, it's actually falling on a really nice spot, right? What would be the ordered pair here? Well, the x value is sitting right here, so the x is at a +1, and the y value is sitting right here, so the y value is at a +2. So I would say that my solution to this system of equations is 1, 2. X is equal to 1, y is equal to 2. And I should really check that, because again, the one thing with graphing, the downfall to doing it this way, is we are really just guessing that this is the ordered coordinates for this point, all right? Because it's very difficult to be exact. So we're going to guess that it's 1 and 2, and what we could do is plug that into these equations and see if 1 and 2 satisfies both of them, all right? So for the first equation, if x is 1, y is 2, this would translate into 2 is equal to 1 plus 1, right? Y is 2, x is 1. So then, does this turn out to be a true equation? 2 does, in fact, equal 2. So yes, it works for that. Now let's check the second equation. So if x is 1, y is 2, this would translate into 2 for the y is equal to a -2 times an x, which we said is a 1, plus 4. What does this give us? 2 is equal to -2 times 1 is a -2, plus 4. And that's going to give us 2 is equal to 2. So there you go. That one checks out as well. So this ordered pair does satisfy both equations, and therefore is the solution to these equations. So we just found the solution without using the elimination or the substitution method. We only used graphing. All right? So it's really a cool way to find solutions. The downfall to it is that, like I said earlier, it's not very precise. We are kind of guessing at the end of the day what the actual coordinate is for the solution. Okay? But it gives us a really good idea. All right. Now, when we talk about systems of equations, there are a couple different things that can happen. So let's first do a couple here and just make sure that you can do this. So, you know, it's difficult for you to do these on your own. Whoops. Just because you might not have graphing paper in front of you. So I will throw this graph up here, and maybe we'll just do it together, but to make sure that you are mentally following through and try to stay a step ahead of me here, okay? So the first equation, y is equal to 2. Let's graph that. Y is equal to 2. That one should be very simple because it just is a horizontal line, right? Y is equal to 2. It never is anything other than 2. So this is where y would equal 2, right along that point right there, right? All right, so that's the first equation. That's easy. Now let's do the second equation. Y is equal to x. Okay, so now here, y is equal to x. What does that mean? Well, it would mean that whatever y is, that's also what x is. If you wanted to use your slope-intercept form, you might think of it as being, okay, it has a slope of 1 over 1, and it has a y-intercept of 0, nothing, right? So it crosses the y then at 0. So and that would be right here. There's where y is equal to 0. And then it's just the slope is 1 over 1. So we go up 1 over 1, up 1 over 1. Again, it's a positive slope. Up 1 over 1. Up 1 over 1. I mean, we can go down 2, right? And we're going to end up with all of these. So we can then draw our diagonal line here. Let's try to move that so it's on our points. There we go. Okay, so there we have our 2 lines. So now we need to find the solution to this system of equations. What's the solution going to be? Well, where do they cross? They cross right here, right? Isn't that the crossing point? Right at this point, right here, right? So what are the coordinates for that point? Well, x is the 2 right here, and then y is also a 2. So the solution is going to be 2, 2. Okay? Now again, as with all of these graphing solutions, we're guesstimating. We're giving it our best guess, and it is something that we should go back and double check. So y is equal to 2. Well, x is equal to 2. There isn't any x in here, so we just have to plug in the y, which we said was 2. So 2 does, for sure, equal 2. So that one checks out. Now the other one, y is a 2, so we plug that in, is equal to x. Well, x is also a 2. Bingo. That one checks out. So that is the solution to this system of equations. All right? Very good. Let's try another one. So I might point out, actually, that both of these last examples, so this first one that we did and the second one thing that we can take away from it is when we're dealing with these systems of equations, they're only going to have one solution when we have linear equations, right? Is there any other point where these 2 lines might intersect as they kind of go off for infinity, you know, in both directions here? Is there any other point at which those 2 lines would intersect? The answer is no. That is the only point that they would intersect. So with these systems of equations, there's only one solution when we have these lines that intersect. Okay? So when they intersect, we call these consistent equations. All right? Which basically just means that there is an intersection point. There is one solution. All right, so this one, again, has an intersection point. It is a consistent equation, or they are consistent equations. And of course, there's only one solution. Okay? Now, let's take a different kind, though. Let's talk about inconsistent equations and what they might be. Well, what I would like to do is, let's take this problem here, and before we graph it and look at it visually, let's use our old methods. Let's take this and use substitution, maybe, to solve for this. Okay, so if we use substitution, let's just say, okay, we know that y is equal to x plus 2. We're going to plug that into our second equation. So if y is equal to x plus 2, then in the second equation, the y can be replaced with x plus 2. So then we'd get x plus 2, that's what we're plugging in for this y, is equal to x minus 1. Okay, now there isn't any multiplication with these parentheses, so we can drop the parentheses, and we're going to get x plus 2 is equal to x minus 1. Now we can do a little rearranging here, just, this is standard everyday solving here. And what's going to happen? We subtract the 2 from both sides, and we end up with x equals x minus 1 minus 2 is a minus 3, right? And now what happens if we want to get the x's to one side? Well, we're going to move this x over, so we're going to subtract it. And on the right side, we end up with a negative 3. On the left side, something very interesting happens. We lose the x, don't we? X minus x is 0. Interesting. I don't believe we've ever seen this before, right? Up to this point. We lost our variable. Okay, we no longer have an equation with a variable in it. And in fact, we even have a false equation. This is false. Right? Because 0 does not equal negative 3. They are not the same thing. And that's what this is saying here. So something went terribly wrong. And at this point, you might go back and go, what in the world did I do wrong? And you might look at this again and look at, did I subtract something wrong? Did I multiply? Did I do something goofy? And the answer is no, you didn't do anything wrong. But the answer is completely false. It's a false equation at the end. So interesting. What does this mean? Okay. Well, to kind of help us with that, we are going to look at it visually. So let's do that. Let's look at this visually. So again, just pulling my graph out. Let's graph these and see what happens. So we've got y is equal to x plus 2. All right, so we're crossing, the y-intercept is at a positive 2. So that's up here. The slope is, again, 1 over 1, and it's positive, so it's going uphill. So up 1 over 1, up 1 over 1. We can go down 1 over 1, so on and so forth. Draw our line. Something like that, right? And then let's graph the other one. Y is equal to x minus 1. So here we're crossing over at a negative 1, which would be, which would be here, right? And the slope, again, is 1 over 1. So we're going up 1 over 1, up 1 over 1, or down 1 over 1, down 1 over 1. And then let's draw that line. There we go. Okay, so let's look at this now. Is there an intersection point? Certainly not in this area that we're looking at on these two lines. Will there ever be an intersection point? Well, the answer is no, there actually won't be. These two lines are parallel, okay? They're never getting any closer together, and they're never getting any further apart as they go off to infinity, in either direction, right? So as they go off to infinity, they're never getting any closer together or further apart. So there will never be a point at which they cross. They do not share a point at any time in infinity. In infinity. All right? So there is no solution to this. This system of equations has no solution. No solution. All right? So that is what's going on here. When we did our substitution, which, by the way, elimination, we'd still end up with the same problem. We'd still end up with a false equation at the end. So if you're doing elimination or you're doing substitution and you end up with an equation that's false, you need to recognize that there is no solution to this system of equations. The lines are parallel. All right? And we give this a very special name. We call these types of systems of equations inconsistent equations. So before we had consistent equations where we did have an intersection point. Now we have inconsistent equations where they are parallel and they never cross over each other at all. All right? Interesting, isn't it? Okay, now let's talk about one more scenario. Actually, before we do that, we've got one more problem to do. So let's go ahead and do this one. And this one, I just wanted to throw it at you because it's not written in the nice, easy slope-intercept form that the other one was. So, but let's go ahead and try it. We're going to do, maybe let's do elimination first on this one. Okay, so let's do elimination. Okay, so if we're going to eliminate, which one do you want to eliminate? We could eliminate the x or the y. I don't care which. Let's eliminate the x. So to do that, let's multiply this top equation by a -1 because then that will eliminate the x's. All right, so if we multiply it by a -1, we end up with -x, -y is equal to a -2. And below we have x plus y is equal to a -3. Okay, now we start eliminating. We have -x and x. That's going to give us a 0. But look at this. The y is also eliminated. Oh my goodness. So we have y 0 plus 0. All right, and I wasn't trying to eliminate those, but they eliminated. And then on the other side, we have a -2 and a -3. Well, that's going to be a -5. So we end up with 0 is equal to a -5, which is very similar to the last problem, right? Actually, it is the last. No, it's not. Okay, so yeah. So once again, we have an equation that is inconsistent. Inconsistent. Meaning there is no solution. Okay? Now, knowing what we know now, what would we expect if we graphed these two lines? What would you expect the graph to look like? Well, if you said parallel lines, then you would be correct. But let's just make sure. So, let's pull out our graph here again. And first thing, we're going to just rewrite this in kind of our slope-intercept form so that we can graph it a little bit easier. So we're going to solve for y. So if we solve for y, we're going to move the x over to the other side. So it's going to be y is equal to a -x plus 2, right? I'm just rearranging. Now, this next one, again, solving for y, we're going to have y is equal to a -x minus 3. Okay? All right, let's graph these two. So, the first one, the y-intercept is a +2. And then we have a negative slope of 1 over 1. So it's going down 1 over 1, down 1 over 1 in the negative direction. All right, so that is the slope. That would be our line. Okay, now the next one, we have a -3 for our y-intercept. So we have -3 is going to be here. And then we have a slope of -1, again, negative slope over 1. So -1 over 1 moves up 1 over 1, up 1 over 1, so on and so forth. And then we draw that line. And yeah, we're looking at parallel lines here again. Okay? All right, very good. Moving on. Now let's talk about a third scenario that we could potentially have when we're dealing with systems of equations. And the third scenario is what we call dependent equations. All right, so what are dependent equations? Well, let's find out. So, same kind of process here. Let's first start with, let's start with elimination on this problem. All right, and just see what happens when we do it algebraically. So if we do it algebraically, and we're going to use elimination, let's try to get rid of the y. All right, and to do that, we're just going to have to take this equation and multiply it by a -2. Maybe I'll put that -2 over here. -2. So multiplying that through, we get -2y plus 2x, right? Because -2 times a -x is a +2x equals a -4. And then below that, we have our other equation, which was 2y minus 2x equals 4. Okay, then we combine these, and we find that there, our y's are gone. That's what we intended, but not intended. And as it turns out, the x's are eliminated as well. So we end up with 0 on the left-hand side. On the right-hand side, we have a negative 4 plus 4, which is 0. Okay, so this is similar to the other problems we looked at where we lost the variables. All right, so we lost both variables here. However, this is not a false equation. This is a true equation, right? So that makes it different than the other ones that we were looking at, right? Because before we had a false equation, this is in fact true. 0 does equal 0. It's just we lost the variable, okay? So what happens when we lose the variable, but the equation remains true? Well, to answer that, let's get a visual on it. Let's graph it and see what's going on here. Okay, so we'll put this here. The first equation, and we'll actually, again, we have to kind of rewrite these so that it's a little bit easier for us. So kind of rewriting both of them, solving for y, we'll have y is equal to, I move the x over to the other side, and I end up with a positive x plus 2. And now the other one, a little bit more work to solve for y here. Maybe I'll just do that over here. I have 2y minus 2x equals 4. Let's get the y term by itself. So we'll move the x term to the other side, and we end up with positive 2x plus 4. Then we divide the y by a 2, and we end up with, divide this by 2, divide all of this by a 2. We end up with 2x divided by 2 is going to be an x. 4 divided by 2 is going to be a 2. So we end up with y equals x plus 2. So, interesting, look what happened here. Y is equal to x plus 2. It turns out that the first equation is the exact same as the second equation. It was just disguised. It didn't look like it necessarily was, but they were in fact the same equation. All right, so if we graph the first equation, y equals x plus 2, we have the y-intercept at a positive 2, and then we have the slope is 1 again, so it's a lot of 1s, 1 over 1, 1 over 1. So this is the slope, or the graph of that line of the first equation, but it's also going to be the graph of the second equation, so they're exactly the same. Okay, so that would mean that, well, let me put it to you. How many solutions then? Do we still have just one solution, or do we not have any solutions, or what's your take on the solution to this system of equation? Would I write no solution? Would I write, unsolvable? What would I write? Well, how many solutions are there here? There's infinite solutions. Infinite. Countless solutions. All right? Because remember, all we're looking for is a solution, which means that there is a ordered pair that satisfies the first equation and the second equation at the same time. And if I go to any point on this line, if I just pick a point, take the coordinates of that, that will satisfy this first equation, because this is the graph of the first equation. But that point will also satisfy the second equation, because this is also the graph of the second equation. So I can pick any point on here, and any one of these points would satisfy both equations. All right? So there are infinite solutions to this particular system of equations. So my answer would be infinite solutions. That would be my answer. Now, we give this kind of equation, or a system of equations, a special name. We call them dependent equations, which kind of makes sense because they're very dependent upon each other. Okay, they're right on top of each other. Okay, so very good. Those are the three scenarios that we can end up with when we're dealing with systems of equations, and they are the only three. So we are going to wrap up today by just doing a quick review now, or a quick overview. Take out your class notebook, take some time, and make sure that you write down all of these definitions for the different kinds of equations that we can get. All right? And then study them so that you can recognize the differences between a consistent equation, an inconsistent equation, and a dependent equation. All right? So the first one, consistent equations. These are the equations that you've been dealing with all the way up to this point. There are equations that have a single ordered pair as a common solution. The graphs cross over, or they intersect at one point, and that point is the solution. And if you use elimination or substitution methods, you will produce true equations that solve for a variable. So this is what you've been dealing with all the way up to this point. All right. Now today we introduced two other scenarios. This is one of them, the inconsistent equation. And that's when the equations have no common solution. They are parallel. The graphs are parallel and they never intersect, obviously. And if you use elimination or substitution methods, you will produce false equations. So the answer is simply no solution if you get that false equation. Okay? And then thirdly, the third possibility here is that we have dependent equations. And this is where the equations are equivalent. They're just kind of disguised to make them look different. All right? They are, in fact, though, the same line, graphically speaking. And if you use elimination and substitution, you will produce true equations, but no variables. All right? Now, before we had an equation that was 0 equals 0. It doesn't have to be 0. It could be 5 equals 5, or 3 equals 3, or something like that. But it just has to be a true equation. All right? Very good. So that kind of sums up the lesson for today. Make sure that you pause the video if you need to and write these definitions down so that you can study them and memorize them. It should become second nature to you. And really, your seat work today will be in OneNote, and I'm not actually having you doing seat work from your book today. I'm actually having a different set of problems for you. So if you go into OneNote, where am I here? We go into OneNote, and if we go to lesson 81, I believe, yeah, lesson 81, you'll see all of your seat work assignment has already been inserted for you. So, there's several different sections here. The first one, they want you to solve each system by graphing. So this is where you're practicing, again, being able to graph lines, but now graph a system of lines and then find the solution for it. Find the place where they intersect, if they intersect. All right? So work on those. And then the next section here deals with the three possibilities when we talk about systems of equations. You need to look at the graphs and then just tell me, are they consistent, inconsistent, or dependent? All right. And then secondly, tell me how many solutions each one has. Is there one solution? Is there no solution? Or is there infinitely many solutions? All right. So that should be pretty easy. And then finally, here I want you to actually identify the solution. So before you were just telling me whether or not they're consistent, inconsistent, or dependent. Now you need to actually look at the graphs and try to find the solution for whatever system of equations these lines happen to represent, and write down your solution. So you'll have to approximate it as close as you are able to, because again, graphing is a little bit of guesswork when we start looking for those solutions. And then I think there's one more section. Yeah, finally, I want you to do some problems here with elimination and substitution. So we're just going right back to what you already know how to do, but based upon how things work out, you need to tell me, after you've done elimination or substitution, is the solution consistent, inconsistent, or dependent? Okay? All right. So that is your seat work for today. Good luck, and then I will see you tomorrow.